Hello, everyone. Welcome to join this online mini-symposium on the mathematical issue of machine learning. It's my great honor to organize this time's first conference on math of data science, and I really appreciate all your efforts and support on preparing this online meeting. And for this session, I think we're going to share the most recent research topics on machine learning and complex systems. I think this is a great opportunity to open the door for researchers from both the computer science and mathematics background to understand the mathematical principles in deep learning or the most recent development in data science and machine learning topics. So the research directions is really involves in many interdisciplinary fields in our session. To just save time for this online meeting, I think I will first introduce Professor Duan from Illinois Institute of Technology, talking about data science plus dynamical systems. What can we learn? This can give us a very promising result from how to extracting stochastic governing laws from SDE, especially for a type of Gaussian-Levy noise. Welcome. Thank you for the speaker.
Okay, good. So you use our video, right? Our video is over there?
Yes, so I've already turned on the video record.
Okay. Yeah, so are you going to play the video?
Oh, yeah, I can play the video. Yeah.
Okay.
I see.
Okay.
Because some speakers didn't upload their video yet.
Okay.
I think for this one, I will share my screen.
Okay.
Can everyone hear and everyone see the screen right now?
Yeah, we can see it. I can see it, yeah.
Okay, great. I will play it.
We can't hear it.
Sorry?
I can't hear the video. Is it?
Oh, I see. Then let me play this way. Sorry, I was plugging the earphone.
This is the joint.
Yeah.
This presentation is about how to learn stochastic governing laws from data. It's also a combination of dynamic systems ideas and data science techniques. So the theme for this presentation, one, is about learning stochastic differential equations with non-Gaussian noise from data. In doing so, we need to derive a non-local version of Cramer's-Moyer formula. The goal is to start with sample path data for a stochastic dynamic system. And then can we find out the stochastic governing law given some data. This is a recent work with Yang Li, and you see in the archive. So the setup, the stochastic governing law, we mean a stochastic differential equation. It has drift. B. Drift is also called a vector field. And this is a Gaussian noise represented by Brownian motion, BT. And this is the so-called Napier noise. It's a non-Gaussian noise. And the lambda is a matrix. Sigma is also a matrix. And so the Bx is called drift. And A is the lambda, the matrix lambda, times the conjugate, or the transpose of lambda. That's called the diffusion matrix. So this is a symmetric matrix. Now, the lateral motion, LT, is represented by a jump measure because the lateral motion has countable jumps. Now, this jump measure has this corner function, Wy. And in this presentation, we assume this jump is symmetric. So W is an even function. So for the rest of the presentation, we'd like to find out B, sigma, or A, and lambda, and what lambda is from A, and W, given the observation or simulated data or experimental data on XT. So that means we have random time series. How can we find out the underlying stochastic differential equation? Now, what is known in the context of stochastic differential equations with Gaussian noise, with Brownian motion only? Well, there are different ways to do it. But for this presentation, I'm going to only mention this Kramers-Moyer formula. And in our archive paper, we have a review for other methods. Actually, for stochastic differential equations, we don't have many techniques to learn. We have some. But this Kramers-Moyer formula is a basic formula that gives us a way to learn stochastic differential equations. But so far, this formula is only true, it's only available for stochastic differential equations with Brownian noise or with Gaussian noise. So this formula gives us a relation or relationships between drift. Drift is B, and the diffusion lambda, or the matrix diffusion matrix A, in terms of sample path data. So sample path data means X, T, omega. So that means if we have observation or simulated or experimental data on XT, and if we know the governing law is a stochastic differential equation, and then by this Kramers-Moyer formula, we can find out the equation in the sense that we can find out B, lambda, and A. We find A. Okay. So this is already known, and this has been applied in different situations in the current context of data science or machine learning. Now, our contribution is to do this for the SDEs with lateral noise. So let's still review the SDE with Brownian noise, with Gaussian noise. The Kramers-Moyer formula, this has been known for a few decades. So this means we can write this drift. So this is a drift. And this is a diffusion. Once you have a diffusion, you can find the lambda, which is the noise intensity for the Brownian motion. So you see this drift and the diffusion are both in terms of sample path data, XT, and this Z is this position, okay, and the initial position is Z here. Now there's a 1 over T here, and take T goes to 0. So this means you take the derivative of this expectation at T equals 0. So roughly speaking, this Kramers-Moyer formula in the Gaussian case is an expression or formulas that give us drift and diffusion in terms of sample path data. Okay. Now, for this presentation, we'd like to do this for a stochastic governing law, but with non-Gaussian noise, sigma DLT. And I call this non-local Kramers-Moyer formula. That's because we are going to see, and the formulas involved with spatial integration. So this non-local. Now that non-local term in the Kramers-Moyer formulas coming from the Levy jump measure, because this is this gives us integration in the generators, okay, and the corner function in the jump measure W is what we're going to looking for. So this non-local Kramers Moyer formulas will give us an expression of B, A, and W in terms of sample path observations. And before we get that, before we get to those formulas, we need to know the non-local Fokker-Planck equation. Now you see, because of the jump measure, we have a non-local term. This is a non-local term in the Fokker-Planck equation. And this non-local term comes from a non-Gaussianity of the lossy fluctuations. Okay. Now, without a non-Gaussian noise, this is what we know, the classical Fokker-Planck equation, or you can call it a local Fokker-Planck equation. Okay. Now this so this, as you can see here, this non-Gaussianity corresponds to the non-locality in the Fokker-Planck equation. And the Gaussian noise only gives us the local version of the Fokker-Planck equation. So if we know the drift and the diffusion and the jump measure, then the Fokker-Planck equation is known. But the problem is we don't know that, right? We only know the sample path observation. So, but this will give us a way to write the B, the drift, A, the diffusion, W, the jump measure in terms of the sample path data. So this is the major contribution for this work. So this theorem says we can write the drift, diffusion, and the jump measure in terms of probability density function. Now, let me go back one more slide. So this P is the probability density function. So P is the probability density function for the solution path X, T, with the initial data X, or with the initial data, which was the initial point Z. That Z shows up in the initial data in this delta function. Okay, so this non-local Fokker-Planck equation gives us the information about the probability density function evolution for the equation, for the stochastic accompanying law. Now, this theorem says, well, without knowing the specific data about the drift, diffusion, or jump measure, or the diffusion, or the time series data for the sample paths, this theorem tells us the information between drift, diffusion, jump measure, and the probability density function. So this is the solution of Fokker-Planck equation. Well, in our case, it's a non-local Fokker-Planck equation. So this, now let's look. So this W is the jump measure for the Leffy motion, for the Leffy noise. Now the left-hand side, now this sigma is the matrix in terms of in front of the Leffy noise. So sigma is the jump diffusion matrix. Okay. So this is minus n. That means it is inverse multiplied by n times. Yes, we assume this this matrix in front of the Leffy noise is non-singular. Okay. Now this P is the solution for this non-local Fokker-Planck equation. So this part one of this theorem says the probability density P, or the solution of the non-local Fokker-Planck equation, is related to the jump measure in this way. Now there's a T here. Look at this. There's a T here. So this really means to take the derivative of this probability density, which is the solution of the non-local Fokker-Planck equation, at t equal to 0. And this is related to the jump measure. Okay. Now, for the Brownian motion driven stochastic differential equation because there's no jump, or the jump measure W is 0. So in that case, the right-hand side is 0, and that formula is known in the Gaussian case. Now the second part of this theorem says that the drift can be written in terms of the solution of the non-local Fokker-Planck equation in this way, and there's a t inverse. So this also means that taking the derivative at the t equal to 0. And also when I say that, that's because I already mentioned this when t is 0, this term is 0. So this left-hand side really means we're taking derivative of this integral at t equal to 0, and that thing is equal to the drift. Okay. Now the third part of this equation of this theorem says the left-hand side is the probability density or the solution of non-local Fokker-Planck equation. Now you multiply these two things, so that means you are thought of taking second moment. But remember, we only do this in a small ball. Okay, so it's not completely a second moment. Now this will give us what? This will give us the diffusion. But now remember, because of the Nephi noise, there is a second part involved. This part is new. This is related to the jump. So this is the contribution of the Nephi noise. It's the contribution of the non-Gaussian fluctuation. Okay. So this is this gives us information between drift, diffusion, jump measure in the stochastic governing law, and the system probability distribution evolution. Okay, can this be used to learn original stochastic governing law? This is what we call the non-local Kreimer-Moyer formulas. Okay, now this gives us the information between drift, diffusion, jump measure, and sample pass data. Sample pass data means X, T. Of course, there's a sample omega there. We often don't write omega, but it's there. So actually, this is a corollary of the previous theory. That's because part 1, I can write the left-hand side of the theorem. Part 1, part 2, part 3, all in terms of sample paths. Because when you do integration using the probability density, that involves a kind of expectation or variance. But remember, we don't have variance here. So that's why there's a jump measure here, jump contribution there. So part 1 says this jump measure can be written in terms of the sample path information. And the second part says the drift can also be written in terms of the sample path information here. Look at this. There's 1 over t taking a limit. Now the third part says the diffusion. Now this diffusion is the noise. It involves the noise intensity in front of the Gaussian Brownian motion. Now there's a non-Gaussian distribution term here. Now this non-local Kreimer-Moyer formulas will give us information about what? About how to compute the jump measure, the drift, and the diffusion. So this is jump and the drift and the diffusion, all in terms of sample path data. Okay, so this is what we can do to learn. So this offers one method to learn SDEs with Nephi noise. I mean, with the non-Gaussian noise in terms of time series observation. So now this the next 3 slides are the numerical algorithms about how to compute, how to find out the Nephi jump measure and the diffusion, which is the noise intensity in front of the Brownian motion, and the drift, which is the vector field for the model, all in terms of time series data. Well, if you have other observations, then that means we need to talk about other ways to learn the SDEs. But for this presentation, we are given sample path data, time series data, and we like to find out the original stochastic differential equation as governing law. So this is to find the jump measure, the left jump measure. Well, once you know the jump measure, you find the left motion. Now this, because this involves what? This look at the previous slide, the non-local Kramers-Moyer formula. So this left-hand side involves what? Involves the first term is to start what you start at any initial. You start at any initial point, and then you like to think out how many points, how many start from Z, and you compute the likelihood this is in this small interval. Epsilon is a small parameter used in the computation, and actually this is true for all epsilon. And the right hand side, we like to think out this curl function. Okay, so this is so the algorithm is in terms of this. Now the second one, the drift. The drift is in terms of what? The probability for the solutions in this small ball and the expectation of conditional expectation of this xi gi. Now the third part is the diffusion matrix. Is in terms of the probability of a solution in a small ball times this expectation. So the next 3 slides are the elaboration of how to do this. And this algorithm only shows you how to do this in 1D, but in higher dimensions will be similar but more involved. Okay, so this means we did this small intervals when we try to count how many points are in fall into the small ball, and then we also compute the expectation for this kind of things. Okay, then we know for this presentation, for this algorithm, we'll focus on alpha stable left motion. It's a special but most significant heavy-tailed left motion. Heavy-tailed fluctuation. So that means we'll find the alpha, and this is the noise intensity in front of left motion. Now the second algorithm is about how to find drift, and this one is for least square minimization. Now the third one is about how to find the diffusion, and also is involved with least square representation. Now this 3 algorithm might not be optimal, but it's one way to do it for dimension. For 1, 2, 3 dimensions, we have examples for those lower dimensions. For higher dimensions, like in any Monte Carlo simulation for moments and or higher moments, there's a curse of dimensionality. So that can be combined with other technologies nowadays. For example, neural networks, for example, to do the higher dimensions situation. So this example 1 is a 1-dimensional case, double well, and we tested our method to find the alpha in alpha stable left noise, and also the sigma, and it tested well. Now the second dimension, 2-dimensional example, we used the Milestone. The third dimension we used the Lorentz, but it's not shown here. So it tested. It appears to be good, to be effective, but it's a lower dimensional case. So in summary, what we have done in this presentation is we derived a non-local version of Kramers-Moyer formulas for SDEs with left noise. Left noise especially includes the alpha stable left noise. That's the most important subclass. With this Kramers-Moyer formulas, we can learn the stochastic governing laws with left noise from a sample pairs data. Thank you very much.
Okay, so thank you very much, Professor Duan. Yeah, about this learning learning-driven SDE. Any questions?
Yeah, can I ask a question?
Yes, please.
Yeah.
Yeah, can you hear me?
Yeah.
Very interesting work. So I missed the exam part for the least square problems. So do you mean that you introduce some kind of basis as capital per psi to learn the coefficients? So where does this least square problem come from?
Oh, okay. Yeah. Okay. Yeah. So to the in fact, in each of those three procedures for the drift, for the jump measure, and for the diffusion, we did a minimization scheme. In this case, we use this as well. So for the jump measure, we have the simulated data on one hand, and the relationship in the non-local Kramers-Moyer formula on one hand. So we match this both sides. In this case, we don't use the basis function. For the other two, we also don't use the basis function in that data, but it's possible to choose a basis. So in that case, we may invoke a kind of sparse sparse learning. In that case, it's possible.
Okay, so in your experiment, how do you use this? How do you choose the basis? Are they like?
Yeah. So. Yeah. Okay. So the question is good about how to do that. In some of our earlier work related to this, we choose the polynomial or trig functions. I remember in one of our newer papers that you will probably see on arXiv next week. With the absorbing boundary condition, we also impose a basis with the absorbing condition. I think that kind of learning is still immature. I like to learn and to find out other ways to better doing the better use this sparse idea. Yeah.
Okay,
it's a good way to think about more.
I might have a very naive question because so this kind of basis learning seems different from the local case. Okay, I mean, okay, suppose there's no jump, you can just use some point estimate to estimate estimate the drift and the diffusion. So there's no need to introduce this kind of basis. So I'm just wondering, okay, in that case, which one will perform better, or what's the kind of possible comparison?
Yeah. Also, we have jumps in the sample passes, but the drift function and the diffusion function, we assume they are smooth. And the only thing is the jump measure. I think that part I don't see an idea to use the basis.
Okay.
Yeah, for the jump part. Yeah.
Okay, thanks.
Yeah. It's good to talk more on that part.
Yeah, I'm done.
Thank you. Any other questions? Okay, then let's move to the next one. Professor Yi from Johns Hopkins University about learning reduced stochastic dynamics on slow stable manifold.
Can you hear me?
Yes.
Okay, let me share the screen. Is it?
Yeah.
Okay.
You got it. Thank you.
All right. So, okay. Thank you, everyone. So today I'm going to talk about how to learn the stable slow manifold. So from in a data-driven fashion. I mean, this is a collaboration with my postdoc advisor, Mauro Madrani, and the PhD student, Sichuan Yang. Sorry, I didn't have time to put the name here. I was in a rush to write the slides. So this work is still in preparation. I'm going to show some preliminary result. Hopefully the paper will be finished in summer. Okay. So the idea, what happened? Just a minute. Let me just, okay. So, full screen mode. So we really want to consider something called like slow fast system of ST. So I learned a lot from Professor Dorn's research. This is a very typical setting. You have fast mode, which is like usually has light stay in ambient dimensions. So living the dimension d, so like big D minus D, it's very big. In a slow dimension, like slow mode, which lives in small d, which is relatively small. So usually it would be 1D or 2D. So like this type of problem is really showing a lot in the molecular dynamics, for example, and in a lot of, for example, and also shows up in the atmosphere sciences. So here, I mean, so the big catch is I have some very small parameter, so epsilon, and my big D is much bigger than small d. So with such kind of system, there are two difficulties. One is stiffness. So like your right-hand side is pretty big. So you need a very small time step to move forward in your solvers. And also has a curse of dimensionality. I mean, since your big D is so big, you need some massive space so like very powerful computer to do the simulations. With some mild assumption with this kind of system, in fact, we can show, I mean, so there's a theorem shows there exists an invariant manifold. The invariant manifold can be parameterized by the slow mode of Y. Then the point is we can reduce this stochastic system on the invariant manifold, which is written as this. So this dynamics for Y, which is precisely something called like so reduced stochastic equations. But how to help, right? So we really think about the whole thing as like black box. So basically you can treat your simulator as a black box. You are going to feed in your initial condition. And it will so each time it will popping out some like trajectories. Then you run, so feeding the same initial condition for n times, it will pop out n like different trajectories. So we denote this for variable as z of t, and we assume all the sample paths start with the same initial conditions. Then you run n like paths, or like we all know, like so one path is not really statistical so relevant. We want to see like a canonical ensemble of n independent paths. So the question is, can I identify the fast mode from data set? Can I estimate something called atlas, which is basically you want to know what is your invariant manifold being so parameterized? And I mean, so the third question is, can we find a simulator on the invariant manifold? So these, if we can answer these three questions, basically we can rebuild the reduced stochastic equations on the invariant manifold. Okay, so really the idea, if you know a little bit, so there's a very traditional textbook, this one, noise-induced phenomena in slow fast dynamic system. I read this a lot. So basically what they do is basically you define the deviation of your sample path from the invariant manifold for the fast mode, which is defined as Kc. Then you just do some linear approximation. Ideally, so you want to, so you can show the deviation is almost follow the Ornstein-Uhlenbeck process, and your slow mode will follow this kind of reduced system. So since we have scale separations, we can assume this Kc quickly relax and reach the equilibrium at the time scale of separation before the drift and diffusion of YT doesn't change too much. So basically, these quantity in the box can be approximated by the constant. So now how we are going to take advantage of this time scale separations, we are going to run n short parallelly sample paths. So there are very key things. First is short. I don't want to run a very long trajectories. And these trajectories or sample paths are independent. So I can run this parallel. I can put like 12 calls, 20 calls, as many calls as you want. Okay, so I only need two statistical quantity, the mean and the covariance of these sample paths. In fact, at the time scale of separation, we can show the mean really behave like this. So it will be a constant, and that constant is can be shown is right on the manifold, invariant manifold, plus a drift term times t, because we assume the drift term on the slow mode can be approximated by the constant. And the covariance is also can be approximated by a constant. That so gamma plus tau times t. I mean, this gamma is the contribution coming from the fast mode. This lambda is a contribution coming from the slow mode. But you can see the contribution of the fast mode, which is basically an OU process, the diffusion constant is almost constant because they already reached equilibrium. But the lambda, and in that part, I said it can be approximated by the constant diffusion and constant drift. So basically the covariance matrix will grow like linearly. Okay, so, and also the rank here for this lambda will be small d, so the rank of gamma will be big D, that's minus small d. Okay, so, and also, I mean, the span of the lambda will be exact the tangent plane for the z, for the z naught, which is z naught is defined right here. So, I mean, all these quantities are really linear. So we can using the linear regression and using the truncated SVD to approximate all these terms, drift like diffusions for this small b here, and the lambda here, and also this like z naught here. All these three quantities can be approximated by the linear regression. Then you truncate to big D minus D. So sorry, so truncate your result to the small d dimensions.
Excuse me, Professor Ye. I think your screen might be stacked over other first two slides, or
Okay, please try one more time.
Okay. Thank you.
Here.
Yeah, it's normal right now.
Okay,
yeah.
sorry.
Thank you. Yeah.
Okay, so basically right here is basic says all these quantity, as I said, for the drift and diffusion can be really approximated by the linear regression. Because this mean and so the mean and the covariance can be really approximated by the linear so everything grows so linearly. So this, I'm going to show this algorithm with an examples. I mean, this is a very interesting example called, so I would call it peanut. This peanut, if you look like, so around some trajectories, you can see this like trajectories quickly fluctuate around. So the invariant manifold. So the fluctuation is very, very big. If you're using PCA in this system, it will fail because it will only capture the fast mode. And because the fast mode fluctuates really, really a lot. You will not correctly find out the slow mode. Okay, and the slow mode is exactly what we want. In this system, in fact, we have two stable fixed point, which is on these 2 points, on this theta and phi, so regions and 3 saddles and one unstable stable point. And basically, it's a double well, but it's a double well in the region of 3D. And so I have a weird shape of manifold, so which looks like peanut. So you want to, so remember, so our goal is from data, we need to reconstruct out this manifold. We need to find out the simulator on this manifold such that your simulation will be restricted on the manifold. Okay, so how are we going to do it? So again, so I'm going to run 10 to the 5 paths for short paths, and the training window for regression is 0.05 to 0.1. Again, this is exactly what I said for the linear regression. Then you truncate, so you perform the truncate SVD for the lambda. But I want to argue this lambda and tau, the span of these two like space is not really pi over 2. So basically, we need to define the inner product to do the projections. If like some point that is away from the manifold, we need to project back to the manifold. But this projection is no longer like Euclidean orthogonal projection. We have to do some to redefine the inner product and project accordingly. So the idea is this B drift and the lambda, which is the drift and diffusions, are almost unbiased. So the difference is is order of epsilon. So this is work in progress. We're trying to prove this mathematically by imposing some constraints. So we have some partial result on concentration inequalities of these estimators. So if you pick one point right here, you can see there will be an ellipsoid and start to grow, and on the odd directions they reach the equilibrium quickly, and they start to move. The whole ellipsoid will be moved along the theta and phi directions. So this is basically, you will see if you run 10 to the 5 simultaneously. This is the thing that you will get. In fact, this black arrow is the direction of the drift, and if I rotate this, you will find out there are 2 arrows of purples, which are correct directions for the diffusions. So you have 1 diffusion direction and 1 diffusion directions on this ways, and the drift is along these directions. Okay, so this orange direction is the fast mode directions, and you can see this fast mode directions is not orthogonal with this plane, which is the slow mode lies on. Okay. So basically, that's what we did for one, as I call it, chart. But then I need to make sure, so I have many charts on this invariant manifold that I can glue these charts together. Right? So I need to define the distance. So the distance is really defined something called, it's very similar to Malahoff-Norbis distance. But this Malahoff-Norbis distance is defined by the diffusion matrix on this point of ZL. But again, I need to symmetrize so that by taking the max for the ZL with Z and Z for ZL. So then I can define something called the local chart. The local chart I call it is 95% of the confidence region of this Gaussian distributions. So you can think about in 2 dimensions. This will be and so basically ellipsoid. Then I'm going to tile these kind of ellipsoid again as 1 by 1 on the invariant manifold, and so I'm going to fill out invariant manifold with this tile of the ellipsoid. And also, basically, I have too many ellipsoid. I'm going to remove some chart that is too close. And I want to make sure these chart can cover the whole invariant manifold. And if I have time, I will mention how to do it with a new mode called exploration mode. And also the third part is I want these chart are connected, right? So such that one has some neighbors somewhere that I can make sure I can track what is neighbor and where can I go through in the manifold. This is partially chart for this manifold in the theta and the phi regions. You can say they are very much connected. There's some region here that is empty. I didn't cover the manifold, but if I plotted it in the 3D dimension, so you can see this partially fill out the invariant manifold pretty well. And also remember, on each chart, I have the information of drift. I have information of the diffusion. Okay, I'm going to using these information to rebuild the simulator on the invariant manifold. So basically, if that's the cases, for example, I start with the point on this red dot, and I know what is the nearest landmark, or the chart is right here. And I know this chart has neighbors, and these green dot are the neighbors. So what I'm going to do is I'm going to ask what is the distance between this red dot with all these neighbors and together with that like nearest chart. Okay, I'm going to weight this distance by taking exponential of minus distance, divide by something with the relaxation time scales. And this says like each landmark, I'm going to, each chart will send me the information. I'm going to weight the information by using the weight given from the distance. Then I'm going to weight accordingly for the drift and diffusions, right? So for each given point, I can find the drift and I can find diffusions very quickly and very efficiently. Remember, everything only lives on the small d, and I don't need to worry about the performance on the big D's. So it will be very efficient and very quick. So this is basically the exploration mode. As I said, if you like randomly sample the point, so it's very difficult to find out these kind of like gap, like maybe this was never explored. So the way we do is we say we have some chart and we let it run this dynamics, and I want to check the distance to the nearest landmark. If it is less than say 1, and I say, okay, wait a minute, I already moved out of the chart. So that's why that will be the point. I need to put a chart or append a chart into my atlas. So this is a very efficient way to sample and to explore some uncharted areas on the manifold. And also, as I mentioned, if we do this analysis, we can show this B, the drift and diffusions are very small. The number of chart that I need is almost 1,721. And you can see this distance for the landmark of the chart is very close to slow manifold. And the drift is very close to true drift. And the diffusion is also very close to the sort of like true diffusions. And then we can find out the maximum norm of drift and the maximum norm of diffusion. We can find out, in fact, my delta t, if I run the dynamics on the slow manifold, I can take a much bigger time step because I don't have 1 over epsilon on my right-hand side now. My delta t can be chosen as 0.03. If you remember what I chosen before, I think I chosen 10 to the minus 4. So which was like, so right now it's 100 times bigger of the time step. So this is a big, like advantage. I don't need to take a very small time step. I can take very big time step if I run the dynamics on the slow manifold. Okay, so a benchmark is really, I want to see whether I can estimate the mean first passing time between 2 wells. So there are like 1 well is here, 1 well is here. This is a saddle point. So like most probable path is like doing something like that. So if I using original simulator, the delta t is 10 to the minus 5. Sorry, so I was talking about 10 to the minus 4. It should be 10 to the minus 5. The simulation hour is 10, so like almost 10 hours. And then we find out the mean first pass time on the top well and the mean first pass time on the bottom well. But if I using Atlas simulator, so our like new simulator, I can take time step of 0.03. Although the training time is a little bit longer, which takes about 20 hours, but the simulating time only took 40 minutes because I take much bigger time step. And we can see the mean first passing time is like within 10% errors of the original simulator. Now only like what you can do is you just save your new simulator, you run your new simulator, you can get, I would say, fairly accurate dynamics as you want. Okay, so that's basically I want to talk about for this. I don't have time to talk a little bit more on the another examples, but I think that's all I want to discuss for this slow manifold learnings. Okay.
Thank you, Professor Ye. Any questions for this?
Just a quick question. Curious. So, what's the most time-consuming part for the training? So, I see the training time is like 20 hours. So,
yes.
So, which part is most expensive?
The expensive part is to run this 10 to the 5 sample path like simultaneously, right, for a very short time period.
Oh, so you mean it's the generation of data?
Yeah, yes, the generation of the paths. Okay. Like basically the Euler things is more expensive. So I run this with a 12 cores cluster. If I have more cores, and I can significantly reduce.
Yeah. Okay, that makes sense. Thanks.
Because this 10 to the minus 5 can be trivially parallel. You just put into different cores. If I have more cores, I can significantly reduce this time.
How did you estimate that error? You said working in progress?
Yes, so the error here is because in this system, the peanut system, I know what is the invariant manifold. I know the manifold is, so the slow manifold looks like that. And I know the drift, and I know the diffusions. I can analytically calculate this. I cook up this example to do some comparison with the drift and diffusions to make sure, this is right. And currently we are doing some like more realistic MD simulations. Once we hit MD, there's no benchmark that we can compare. We don't know what is the true slow manifold. What is the true, dynamics on the true slow manifold. I have no idea. So for this peanut example, I know what is the B drift. I know what is diffusions. Then I can compare with my estimate B and estimate diffusions with the true Bs and the true diffusions.
Yeah, I also have a question, maybe simple, about the sample data you collected. Yeah, for the sample data, does the time window need to be on the same time interval that you chose from, like for example, 0.5 to 0.5? Yeah, 0.1.
0.05 and 0.1. So okay, so I didn't mention how to choose the Okay, so this is a very good question, in fact. So this question is coming from how to pick the time scale separations. This S1 and SM has to be in the region of time scale separations. That means the fast mode already reached equilibrium, the slow mode, it doesn't change too much.
Yeah.
In order to find out this time scale separation region, what we can do is, in fact, we can find out the trace of the covariance. And I didn't, so put here, there's a various way that from data you can visualize to see what is the time window you should choose to find out the scale of separation, because different problems have different time window for you to do the time scale separations? I mean, this is a very good question, and I mean, to choose this time window correctly is very, very crucial and to get it right.
I see. Okay. Yeah. So when you like get some simulating data to find this time window, and all the like for your system, you just choose this time window. But for other high dimensional case, that's
there are some ways to do this. For example, you can plot the trace of covariance. Like, so now the covariance matrix so it's changing along the time. So you think about the one point, and your data is start to grow. So what you can do is you can plot the trace of your covariance, which is the sum of all the variance in each component, and you will see the trace will grow non-linearly initially, then will grow linearly. Once they grow linearly, that means the fast mode already reached equilibrium. And the slow mode can be approximated by the constant driven and constant diffusion. So this, we have done that. So this can give you a very strong indication of the time scale separations just coming from the data.
I see. Thank you very much. Any other questions?
So in fact, this whole idea, so when Professor Duan visited Hopkins last year, and I was talking to him, it helped me to sort of a lot of ideas. Probably don't remember the details.
I remember.
I do learn a lot from your previous work.
Thank you. Okay, thanks. Very interesting.
Okay.
Yeah.
Great. Yeah, I think we can like have more discussion afterward if anyone interested. So let's welcome the next speaker, Professor Han from Princeton, talking about the deep learning bridging the solving high dimensional PDE to the forward backward SD. Thank you.
Can you see my screen?
Yes.
Okay. Thanks for the organizers to make this virtual symposium happen at such a hard time. So today I'm talking about DUBSD as a unified framework for solving high-dimensional PDEs, FBSDs, and control problems. In particular, I would like to highlight its potential in solving large-scale games, which it has been untractable in the general case for a very long time. So let's start from background. So the central topic of my research is dealing at least 1 year in dealing with high-dimensional PDEs. So here I just list 3 motivating examples. The first one and the second one somehow similar. Okay, the first one is having the Jacobi-Bellman equation derived by the dynamical programming. So here I list 2 versions. One is in continuous time, one is in discrete time. V is the value function to be optimized, and X is some state variable. The second one is the Black-Scholes equation, widely used in financial industry for pricing financial derivatives. The V is so-called value, and the X is the price vector for the whole basket of stocks on the consideration. And the third one is the Schrödinger equation to characterize the quantum many-body problems. So here the capital phi is so-called wave function. If we can solve this wave function, basically we have everything we need to know regarding the systems. So if you take a further look at these kind of equations and more examples, you will realize a common feature is that the dimension of these equations can be easily large in practice. Okay, for example, for the HJB equation, the dimension is the same as the state space. So if you are dealing with real complex systems, the dimension goes up very quickly. For Black-Scholes equation nowadays, okay, the dimension is the number of underlying financial assets, and nowadays, okay, it's very common to price some derivative based on, for example, 100 stocks. And for the shorting equation, okay, in practice problems, the dimension is roughly 3 times of the number of electrons if you are considering real space. So even if you want to solve a wave function for a single water molecule, for example, the dimension is already 30. So from a computational perspective, the key challenge is so-called curse of dimensionality. Okay, namely the complexity exponential in dimension d for most numerical methods, including find difference, find element. Okay, the process limit you can argue, but usually these kind of methods will become unavailable when d is larger than 5 or 10. Okay, and this is far away from what we want. So in other words, there's a huge gap between modelings and the computational algorithms. So actually, upon the development of deep learning, okay, nature we have very limited tool sets to deal with high dimensional PDEs. Okay, one probably the most motivating examples is the Feynman-Katz formula for dealing with linear parallel PDEs. Okay, if we consider a linear parallel PDE, okay, it's in standard form with time variable from 0 to capital T with spatial variable in the d-dimensional space. So this is a PD, this time derivative, this the second order derivative, this is a drift, and this is some kind of nonlinearity. Okay, following the convention, we assume the terminal condition is given at capital T by Gx. So that's why the time derivative and the second derivative share the same sign. Okay, the point is that we can consider SD derived from this PD. Okay, here the SD is forward with drift mu given by the PD and the diffusion sigma given by the second order term of PD as well. Then the famous Feynman-Katz formula tells us that the solution of U can be expressed in terms of some expectation involving the terminal cost G and the running cost F, both from the PD, F and G, and conditional on the initial point xt equals x. Okay, in this case, in order to get some solution at a specific point t and x, we can just simulate a lot of forward SDEs. Okay, then we use Monte Carlo simulation. We can use Monte Carlo approximation to approximate the expectation, and we get a solution for you. So this kind of algorithms is mesh free. You do not need any discretization of t and x, and in this sense, it overcomes the curse dimensionality. Okay, but this nice thing only happens for the linear case. If we go one step further, consider a general semi-linear PDE. Okay, which is widely used for a lot of modelings. And here the PD is almost the same as in the linear case, except that the F, nowadays involve more terms, including the U and the range of U, up to some transformation determined by sigma. The same terminal condition is applied. And then if we consider the same for the process, because the mu and the sigma is the same, determined by drift term and different term, we can apply the Ito's lemma and check the solution of PDEs. We immediately derive the following result. So this is similar to the linear case, but here it's no longer a martingale. The martingale part is the same, but you have a drift term F, coming from the PD itself. So this is a simple practice of Ito's formula. So you can see the Feynman-Katz formula cannot be used directly, because if we want to simulate this process, to get a conditional expectation, for example, initial time 0x0, we need some information of U in the middle in terms of U itself and the gradient. So it's like a chicken egg and problems. You cannot simulate this SD directly. So that's the main challenge when dealing with semi-linear PDE. And another viewpoint to look at this formula, you can replace the U, the U variable, UTXT variable with another variable denoted by Y, and replace the gradient of U with another variable, for example, with Z. You can write this kind of backward SDs. This one is backward because the terminal condition is given. And this is the forward part, same as before. So this is called the forward-backward stochastic differential equations. And this kind of systems essentially give us a nonlinear version of Feynman-Katz representation for the nonlinear parallel PDEs. So from control perspective, it is related to Pontryagin maximum principle. And if you are from PD background, you can interpret it as some kind of characteristic methods for decoupling nonlinear parallel PDEs. Okay, and we will based on this kind of systems to develop numerical algorithms for solving high-dimensional PDEs. So, okay, let's recall the connection between the PD and the BSD. Okay, so the Y is related to the solution of U, and the Z is related to the solution of the gradient of U. Okay, so if we look at these variational problems, okay, so let's start from the constraint. The constraint is the same as the FBSD, except that here we drop the terminal condition of YT. Okay, we rewrite it as a terminal forward process. Okay, so with under Y0, so we drop the terminal conditions and we put the terminal conditions into the loss functions. Okay, so we examine the difference between the terminal value of Y and the given terminal conditions. Okay, so looking at these variation problems, if we plug in the solutions of the two BSD, okay, and we find, okay, the constraints are satisfied and GXT equals YT almost sure, so the loss function is 0. So in other words, we know the two solutions of the BSD achieves a minimal value of these variation problems. Furthermore, the well-posedness of this FBSD tell us, okay, the unique minimizer provide us the solutions of the BSD, so as well the solution of PD. So in other words, if we can solve these variation problems, okay, we can get the solution of PD. So this is the starting point of our numerical algorithms. And to make it attractable by computers, so we need some kind of discretization. So first, noting that the arguments here, Y0, unknown variables, Y0 and ZT are just processes, so are infinite dimensional. And we make it finite dimensional by some function approximators, and in particular, the deep neural networks. So we use two neural networks, percent phi, to approximate the unknown variables, unknown process Y0 and the ZT. Okay, the primary reason to consider deep neural networks is because it's very effective when dealing with high dimensional functions. And remember that here our input variable X can be high dimensional, like 100, you will see in a minute. So networks provide us, okay, promising candidates. And then next thing is to discrete a time variable, okay, with some time, for example, in this case, Euler scheme on a fixed time grid. Then we can write out these finite dimensional optimization problems instead, okay. Here, this is the parameters of neural networks. So these are just a simple discretization of for the SDEs for XT and the YT, okay? And we want to optimize the parameters of the neural networks. And you can see at each time t, we have a subnetwork mapping the x variable onto the z variable, the gradient of the u, okay? The interesting observation is that we can stack all the subnetworks together, okay, to form a very deep network as a whole based on this time discretization. So this is a schematic plot of the whole graph. So each column corresponding to a time grid. The bottom process are the forward X process and the Brownian motion. And here the green components, okay, are the hidden nodes of neural networks, giving us the mapping from the XT to the gradient of U. And then this is the backward part of the SD, and we finally get the output of U. So this is kind of the output of the whole neural networks. And then the matching between the terminal condition and the output of neural network give us a natural loss function to optimize, okay, in terms of expectation over the Brownian motion. So from machine learning perspective, you can think the path of xt and wt as the input and this u hat, okay. Something we want to matching is the output of the network. Okay, since this kind of forward path xt and wt can be simulated easily, so we can leverage the commonly used SGD algorithm to optimize this loss function. We just simulate a mini batch of process and take the gradient step, stochastic gradient descent step. We call the whole methodology as deep BSD method, since we use BSD and deep networks as essential tools. So let's take a look at a few examples. So this is a classical linear quadratic Gaussian example in the 100 dimension case. So here the lambda is some hyperparameters, denoting the strength of control, and MT is the control. And this loss functional is quadratic in terms of MT, and together in addition with some terminal cost. So due to this quadratic structure, we can write out the HJB equation explicitly, and by some Ito's formula, we can check. We have some expectation formula to present the solution of this HJB. So this allows us to do the accuracy test. And you can see our DBSD method achieves a relative error at a single point, okay, when lambda equals 1, with 0.17% relative error in a runtime of 300 seconds on a single MacBook laptop. So this is quite impressive, okay, consider the 100-dimension case. And if we change this lambda, okay, if we change different problems, you can see our algorithm always give some reliable solutions in this simple case, okay. In simple case, for this the single point we are considering. Second example is the Black-Scholes equation. So I think this is the most widely examples of people are interested in high-dimensional PDs. So here we consider a special case for recursive variation model with default risk. So we are pricing some fair price of a European claim based on 100 underlying assets conditional on no default having occurred yet. So by some modeling, you will find that, okay, we need to introduce another nonlinear term on the top of the standard Black-Scholes equation. So this term is nonlinear because the Q, the intensity of the possible default, is nonlinear functions, okay? So we check the performance of our D2BSD method, again, on a single point. So you can see it achieves a relative error of size 0.46% in a runtime of 600 seconds, again, on a laptop. The last example is an oscillating example. Okay, in literature, people consider the case D equals 2. Okay, but we become ambitious, so we again test the 100-dimensional case. So this PD is constructed artificially. The main feature is that, okay, it has some oscillating explicit solutions. So that's a sign term. For this example, we did an ablation study. So we test the relationship between the final errors and the number of parameters, in particular, the number of layers. So you can see, if you recall our algorithms, we use neural networks to approximate the Y component and Z component. So if the depth is very limited, because it means that we have very limited capacity to approximate the unknown functions. So in this case, you can see the error is relatively large. And if we increase the depth, so here the depths are all the multipliers of 29 because the time utilization is 30 times steps. So this means we have 1, 2, 3, 4, 5 depths for each subnetwork at each time steps. You can see as the depth increase, our error decrease, but okay, it will get saturated at some point. So this is just one thing I want to remind you. This kind of common feature for deep learning based algorithms for PDs. The error will get saturated, unlike going to 1 to the -6 or 7 in traditional numerical methods, because our SGD optimization has some kind of limited accuracy. Another aberration study is that we test the effect of different activation functions, and you see, okay, on 3 testing problems, our performance is quite insensitive to different choice of activation functions. Okay, so this shows the robustness of the DBSD method. And so here, next I will talk about the application in game theory, okay, which is the interesting part of the talk, I think. Okay, a lot of games, okay, in stochastic case can be modeled by this kind of stochastic differential games. So here we consider a large stochastic process. We use capital XT to denote the n-dimensional common state process, okay, observed by all the players. So here there are n players, and the superscript alpha denotes from alpha 1 to alpha n denotes the collection of all player strategies. And so naturally, for each player I, given other strategy, the player I want to choose optimal strategy alpha I to minimize his or her costs, okay, in a standard form, some running costs and some internal costs, okay. So this is the standard formulation of stochastic differential gain. Okay, by the dynamic program principle, we can write down the HJB systems, define the Markovian Nash equivalent. Okay, so here it's just systems of large PDEs. For each player I, it has a value function, okay, by superscript I. And so this is standard HJB equations. If we find the HJB solution of this HJB equation, we find the Markovian Nash equivalent. Basically, if everyone follows their strategies, no one has the incentive to deviate from the solutions. Okay, so we want to solve it numerically because okay, you cannot hope to have analytic solutions in the general case. So this is systems of large PDEs. In principle, you can still apply a deep BSD method directly. You can still have the connection between the PD and the BSD, but you will realize quickly it is very memory consuming as number of agents n increase, because in general, okay, the dimension of x variable x, okay, also will increase as n increase. So it becomes memory consuming if the number of agents is not so small. So the key idea comes to rescue is to decouple the problems to each player, assuming all the other player strategies alpha minus I, okay, except alpha I are all fixed, okay. So then if all the other players strategies are fixed, then we only need to solve one equation, Vi, okay, at one time. So we can apply the deep BSD method directly, just as in the linear quadratic example I show you. Then we repeat the whole iteration, okay, and we hopefully we will see some convergence give us the solutions of the Markovian Nash equivalent. So it is just like the Jacobi method for numerical linear algebra. You fix all the off-diagonal components alpha 1 to alpha n except the diagonal part alpha I, and solve the diagonal part alpha I and iterate until the convergence. So it is called fixed play in game theory. So in one word, we combine the idea of deep BSD and fixed play, and we call the methodology deep fixed play. So this is a pseudocode of the deep fixed play. You can see there are 3 levels of iteration. The first is just the round index of the fixed play. So you need you need some iteration, and the middle level of iteration is solving n+ game. So this part can be parallel if you want to pursue further efficiency. And for the inner level, it's just the HG upper iteration for solving deep BSD variational problems. So here I want to show some examples. So this example is the interbank borrowing and lending games. Okay, you are modeling the behavior of n banks, so they can borrowing and lending with each other with this alpha term. So this is a linear term, and you have a control. So this is A, okay, the linear term, and you have alpha term modeling your behavior with respect to the central bank. You can either borrow or lending. And the W0 is some common noise applicable to each banks, and WI is individual noise for each bank. So this kind of game can be put into the framework of the huge SDs I described, provide this kind of drift functions and diffusion functions. If we further assume the cost function is quadratic, then it is essentially the linear quadratic game. So we can have some analytic solutions to benchmark our new algorithms. Okay, although our algorithms is much more general beyond the linear quadratic case. So here is the numerical results. We consider a 10-player games, okay, which is quite challenging in general. So here, the top column is the sample path of the X process given by the true solutions and our numerical solutions, and the bottom column, bottom is the control process. So here, the solid lines are the true solutions, and the dotted lines and the dashed lines are the numerical solutions. So you can see they agree with each other quite well. So next, we can further even consider a risk-sensitive version, which is quite important in financial industry. So here, the loss functions, cost functions becomes risk-sensitive. Okay, provide this risk-sensitive parameter theta I. Okay, so we can apply the same methodology. So here is a similar figure. You can see, okay, this is slightly worse than the previous figure because this problem has more nonlinearity. But in general, the numerical solution still agrees with the true solution quite well. Okay, XT is quite consistent. and for control, for next order control, it has some kind of error. Okay. And the last numerical example I want to show is the most exciting one. So if we replace the dynamics, okay, with the linear part with some cubic part, okay, so now these problems becomes untractable because it's no longer linear quadratic. No simple solutions is available for the PDEs. Even you consider the mean field limit, okay, which is another approximation strategy, you still have difficulty in solving the mean field game, because here you have some common noise. So the mean field limit is still infinite dimensional. Okay, but we know the mean common noise is very important for financial and economic applications. So basically, for this kind of game, we do not have any numerical solutions. So as far as I know, our algorithm provides the first feasible numerical solutions for to deal with these kind of problems. Unluckily, we do not have the true solution to benchmark our accuracy, but at least from this kind of histogram, we can see our numerical solutions is reasonable in the sense that, okay, due to this cubic term, the process will come back to the center, the mean, okay, with faster pace. So you can see the superlinear drift case, we have a more concentrated histogram. And similarly for the control part, because this term will provide more force to pull it back to the center, we can save some costs in the magnitude of alpha to reduce the cost. So you can see the histogram of alpha is also more concentrated compared to the linear case. Okay, I like to mention, okay, this is case for the 50-player games, so which is very challenging for numerical solutions. Okay, I think I will skip the theoretical parts. I have already uploaded the slides. You can check it if you feel interested. So far we have two kind of theorems for this method. First, we have a posterior estimation. So if our loss function is really small, okay, we can confidently claim that our solutions is also accurate. And the second is some kind of upper bound for our optimal loss. Okay, if our target functions falls into some nice class of functions, okay, attainable by the universal function approximator, for example, like neural networks, then we can assure you that the loss function can be very small. Okay. So as a summary, okay, so these are the reference mentioned. So here today I only talk about the application of deep basic method for financial applications and the games. It can also be used to solving discrete control problems. Okay, this is the earliest work dates back to 2016, and it can also be used to solving elliptical problems like eigenvalue problems. Okay, following a diffusion Monte Carlo approach. So this is a range work. In summary, deep learning is providing us really powerful tools to overcome the chaos of dimensionality in high-dimensional parallel PDEs and control problems. For the general nonlinear parallel PDEs, the methodology is to reformulate the PDE problems into aberration problems based on the BSD formulation and approximates the unknown components by neural networks on either solution or the gradient of solution. The similar methodology can be applied to solve model-based control problems. Okay, you can either imagine that in which the optimal policies are approximated by neural networks. So we have a lot of numerical results validating the proposed algorithms in high dimensions in terms of both accuracy and speed. So we believe this will open up the new possibilities in a lot of disciplines, including economics, finance, operational research, and physics. So thank you very much for your attention. Yeah, I'm done.
Good. Yeah.
Thank you very much, Professor Han. Any questions for this?
Yeah. So your convergence, what does it mean? Does it mean that neural networks converges to your solution, or BSD converges to your PD, or both combined?
Okay, I think the first one is irrelevant to okay, so they are both related to the time discretization and the function approximation, but the result is kind of independent of neural networks.
Neural network.
Yeah, for first theorem, so here the y hat is our time discretized process, and xt is the original process. So we show that, okay, as long as our our terminal loss functions so based on our time declaration and arbitrary function approximation. As long as the loss functions is very small, okay, then we can claim our numerical approximation is very accurate. So this is why we call it a posterior estimation, because this is something we can check. If we know it's very small, then we know.
Yeah.
Okay.
So this estimate does not require the layer of neural networks to be large.
To be large. Yeah.
That's not good. That's
So then, so that's reduce. That goes leads us to the second theorem. Okay. Then.
Second theorem. Okay.
Yeah, we can naturally ask. Okay, is it possible to achieve a very small terminal loss functions? Okay. So then here I give us an upper bound for this terminal loss in terms of some difference between the true process and something of the continuous problem itself and our function approximators mu0 numerals and 5 parameters. Okay, so here it means if our target function is y0 and here some continuous expectation can be well approximated by our neural networks, then at least we can claim there exists some neural networks such that the loss function is very small. But here, right now, the optimization process of this whole algorithms, okay, this is quite challenging even for the supervised learning. So yeah, we cannot, claim, we can with high probability find such kind of neural networks. We can, so far we only claim there exists some nice neural networks to serve this purpose. Yeah.
Yeah. Okay. Thank you.
For giving me the opportunity to this clarification.
Okay. Thanks.
So I have a quick one. So I saw the network architecture here. So the first question is, you said it's solving parabolic PDE. Is it like so can be used to solve the wave equation, high dimensional wave equation stuff?
I think for the hyperbolic right now, this kind of methodology is not applicable because here we are highly utilizing the equivalence between the BSD and the parabolic PDEs. But for wave equation, as far as I know, we don't have this kind of equivalence. So the wave equation is a completely different story.
I see. So the second question is, so can you say anything about the stability here? If you're using the Euler method and you choose very small delta t to make sure it is stable, is there any relevant to the choice of the neural network parameter here? So like with the neural network, so is it possible I can choose a bigger time step?
Oh, I don't think so. Okay, I can answer this question from two perspectives. Okay, numerically, actually I open source the code. Okay, the code is available on GitHub. GitHub actually for auto problems we test that. Okay, in order to achieve certain accuracy, you have to apply enough time declarations. Otherwise the accuracy, the approximate accuracy, it will be largely affected by this time declaration. Okay. On the other hand, actually you can easily see this time declaration effect from the theorems we are proving. Okay. For this posterior estimation, to make it meaningful, there's also another term contributing to our problem, the edge. Okay. If the edge is large, there's no hope. Okay. We can get reliable solutions.
I see.
Okay. Thank you. So I would say let's move on because time is almost limited. Let's welcome Professor Parthik from Lawrence Berkeley National Library, talking about the data-assisted forecasting of chaotic dynamical systems. And Professor Parthik, do you want me to share your uploaded video?
No, I think I'll just do the presentation.
Oh, sure, great.
That seems to be. Thanks a lot for the introduction. I'm a postdoc. I'm not a professor. Just wanted to clarify that.
Great as well.
Thanks. Can you guys hear me properly?
Yes.
Okay, I'll pull up my slides in a second. Yeah, thanks a lot for inviting me to this talk. Sorry, I'm just going to adjust my screen a little bit. Okay. Yeah, I'm Jerry Pathak. I'm a postdoc at Lawrence Berkeley National Laboratory, and I'll be talking about data-assisted forecasting of chaotic dynamical systems. I've joined as a postdoc at LBL it's only been a few months, so I'm going to be talking about my previous work that uh, that was as my part of my PhD thesis at the University of Maryland. Right, and so my collaborators on this thesis were from University of Maryland and from Texas A&M University. With that short introduction, let me begin. So the key question that a lot of people, including myself, are interested in is that what can we infer about a chaotic dynamical system from observed time series measurements made from the system? Sorry.
Is there a problem there?
Can you not hear me?
Yeah, it's very noisy.
It's very noisy.
So I can hear.
Okay.
Well,
It's quite clear.
Okay. Can you mute your mic if you're not speaking in general?
Sure.
Thanks. Is it better now? Can you hear me better?
Yeah, it's better.
Okay, perfect. Thanks a lot. Yeah, so the key question that a lot of us are interested in is what can we infer about a chaotic dynamical system from observed time series measurements obtained from the states? If you have a dynamical system and you have access to the observed time series measurements of the state and you don't completely know what the exact equations governing the dynamics are, or if you have only partial information about the equations governing the dynamics, then the question is, what can you infer about the system? So I'll be talking about using machine learning approaches for data-driven analysis and forecasting of chaotic dynamical systems. And here's a brief outline of what I'll be talking about. First, I'll begin with describing the technique for short-term forecasting of chaotic dynamical systems using an algorithm called reservoir computing. It's just a very simple form of a recurrent neural network. It's much less sophisticated than state-of-the-art deep learning techniques for recurrent neural network design that you may be familiar with. But it does the job pretty well, and you can take it very far and do some very interesting things with it, and I'm going to talk about those things. Then I'll talk about scaling the machine learning setup for forecasting arbitrarily high dimensional chaos. Specifically, I'll be talking about how to parallelize these architectures and how to do something called data-assisted forecasting, where you use a model in conjunction with a machine learning setup. And then I'll talk about extending these techniques to the three-dimensional atmosphere for numerical weather prediction. So this will sort of tell us that the techniques that we have been developing are not strictly limited to toy problems, but you can actually use them on real weather data, which is a problem of like a lot of interest to a lot of to all of us basically. And finally, I'll end with some comparison of deep learning architectures for the problem of chaotic dynamical systems, problems related to chaotic dynamical systems. So, introduction to reservoir computing, or what reservoir neural networks are. So it's a very simple setup, which is a network of D sub R nodes. So as you can see in the picture, you have these DR nodes with the yellow dots denoting the network nodes and the arrows denoting the weighted directed connections between the nodes. Each node I has multiple inputs and outputs, and it has each node has a scalar state denoted by R sub I of t. And if you put all the scalar states of these DR nodes together, then you get a vector R of t, which is the state of the reservoir computing network. The weighted connections between these nodes will be represented by an adjacency matrix A, which is obviously DR. It's designed to be sparse for computational efficiency. It's randomly generated, and and untrained. So these connections will not be trained during the course of our of our simulation. They are randomly generated, so you will essentially initialize a random network, and then you won't change it after you have initialized it. So how do you train this neural network? Let's look at that. So for training, you couple an input to the reservoir network through a fixed randomly generated input matrix Win. So you already have a random matrix A, which is the reservoir adjacency matrix. You have another input matrix, which is like an input layer, which is Win, which is also fixed and randomly generated with some hyperparameters. And you couple an input U of t to this reservoir network through this input layer. Then you drive this reservoir layer through this equation that you see on the screen right now. So the reservoir dynamics has two different components. One of the components is external forcing through the input, which is the second term in the brackets there in the hyperbolic tangent. And it also has some self-excitations and some internal dynamics due to the first term, which is A times R of t. Yeah, and obviously the hyperbolic tangent provides a nonlinearity. Otherwise, this would be a linear neural network. And finally, yeah, so for a period from minus capital T to 0, so for a time interval t, you have this training data, which you are going to feed into the reservoir computing neural network and let the reservoir computer evolve according to the dynamics and record the states of the neural network, R of t, in this interval. Following this, you're going to find an output weight matrix W out that minimizes the following loss function. So now this is the final output layer, which is going to be trained. So this is the only trainable layer in this network. W in is fixed. The adjacency matrix of the reservoir is fixed, but W out, which is the output layer, is going to be trained by minimizing a simple least squares loss function that you see over there. Nothing very fancy about it. In fact, it does not even require backpropagation. It's a simple linear regression problem, as you might expect. So yeah, that's what sort of makes it very useful for, as you might be aware, when you have trained, if you have trained recurrent neural networks, it's very time consuming. It takes a lot of computational power respect to anything that's any non-trivial task. But with reservoir computing, you can train them pretty fast compared to other recurrent neural networks. And so what are we training this network to do? We are training the network to do a one-step prediction on the input. So if you give it U of t, then your network should give you U of t plus delta t. Right. Any questions at this point? Okay. Let me move on then. And then finally, in the prediction phase, the network runs as a closed loop feedback system according to the equations that are on the screen right now. But essentially what happens is that you connect the output of the network to the input. So what happens is that the reservoir computing network generates a one-step prediction from U of t. It gives you U of t plus delta t. It feeds that prediction back to itself, and then it generates another prediction U of t plus 2 delta t, then feeds that back to itself, and you get U of t plus 3 delta t, and so on and so forth. So now the network has become an autonomous dynamical system, which is reproducing the characteristics of the data that it was trained on in an autonomous fashion. So let's test this network on something called the Kuromoto-Sierpinski system. This is a non-linear spatiotemporal chaotic PD that you might with. It's defined by the equation, by a partial differential equation that you see on the screen. It's defined in the domain 0 to L, and it's periodic in this domain. The reason we choose this system is that it's a paradigmatic model for complex spatiotemporally chaotic dynamics when you have spatially extended systems. On the screen, you see a picture of a typical trajectory of the Kuromoto-Sierpinski system. On the y-axis, you have the spatial extent from 0 to L, and on the x-axis, you have the time. The color here indicates the value of the spatiotemporal field y of x comma t. And as you might see, might have noticed, the time is denoted in units of lambda max times t, where lambda max is the largest Lyapunov exponent. and 1 over lambda max is what we call the Lyapunov time. The Lyapunov time defines a very characteristic time scale, which is relevant for chaotic dynamical systems, particularly when you're considering prediction tasks. Because in one Lyapunov time, errors in a chaotic system will grow on an average by a factor of E. So because you know that no matter how good your model is for a chaotic dynamical system, if any initial error that you have in the initial conditions, that error is going to grow exponentially. So on a time scale that is defined by the Lyapunov time. So anytime you say, oh, I can predict a chaotic system for some time, you have to compare that time to the Lyapunov time, which will tell you whether the prediction is trivial or non-trivial. If you are only able to predict a chaotic system for, let's say, a fraction of a Lyapunov time, then you can argue that, okay, over that time scale, the system is sufficiently linear or doesn't have this exponential error growth characteristic. So like that prediction could be discounted as trivial. But if you are able to predict a system for multiples of the Lyapunov time, then you might be able to call it a significant non-trivial prediction. So here's some of our results for prediction of the Kuromuro sufficiency system. On the top panel, you have the true state. The second panel shows you the reservoir computing prediction. And in the third panel, you see the difference between the reservoir computing prediction and the true state. As you can see by the color scheme, the color green in the third panel indicates a value close to 0. So you have very low error for about 5 multiples of the Lyapunov time. And so we say we get good prediction quality for about 5 multiples of the Lyapunov time, which is pretty good because it's a non-trivial prediction. It's on a time scale where you have the full extent of the chaotic dynamics visible in the system, right? Which is very good, and but we are interested in very high dimensional chaos. So we want machine learning to be useful for studying very high dimensional dynamical systems, and we are not interested simply in solving toy problems, but we need to be able to extend it to systems like turbulence and general circulation models of the atmosphere, or things that are actually relevant and interesting in doing actual science. So we asked the question, can machine learning be useful for studying very high dimensional dynamical systems? Because interesting dynamical systems, such as atmospheric general circulation models, are very high dimensional. This leads to the question, like, why is it a difficult problem? Why is high dimensionality a bad thing, or why is it a difficult problem? Because it's pretty intuitive. As you increase the size or complexity of the dynamical system, you're going to need a bigger neural network, and that's very intuitive as well. You know, you have a more complex dynamical system, you need more computational power in some sense, and often that comes from increasing the size of the neural network. And if we keep increasing the number of nodes, the training problem can become intractable. So one of the solutions is pretty straightforward, that we use some knowledge of the physics of spatiotemporal systems, that namely that our system has short-range spatial correlations, and due to this, the training prediction of chaos can be very effectively parallelized. The way we do it is by using multiple reservoirs and by using parallel computing on a cluster. So each reservoir is going to be assigned to a local neighborhood on the spatial grid, and it's going to be trained to predict a subset of its inputs. In the cartoon that you see on the screen, for example, the middle reservoir is being assigned to this local neighborhood consisting of the 4 grid points that have red arrows coming out of them. And it's being trained to predict only 2 of the grid points, the values are only 2 of the grid points. So that's how you like divide the domain or decompose the domain into like independent blocks with some overlap. And this overlap is extremely essential in order to take care of the short-range spatial correlations. Without the overlap, the system would not work. And each of the relatively small parallel reservoirs has its own relatively small independently trained output matrix. So all this training can be done in parallel on a computing cluster. And then when you go to the prediction phase, a given reservoir, I mean, as we saw in the earlier case, we have to close the loop. You have to close the feedback loop in the prediction phase. But when we close the feedback loop, we have to be careful in the parallelized case, because a given reservoir has feedbacks not only from its own outputs, but also from outputs of the neighboring reservoirs on each side, in order to account for the buffer zones or overlaps. So this is this introduces some amount of sorry. This introduces some amount of communication between your parallel cores, and but we find that it does not affect the scaling as much as you would expect. You still achieve high scalability despite adding some communication overhead between the parallelized cores. So here's a result for prediction of high dimensional chaos, where you have again Kuromura Sufficiency system with this time the domain size is L equals 200, and the Kaplan-York dimension is 43, which is a very high dimensional attractor, and you are able to predict for pretty close to like 5 or 6 Lyapunov times, and this is achieved by having 64 reservoirs in parallel, each of size 5,000 nodes. This would not be possible with a single reservoir because you would soon run out of like processing and memory issues. I mean, so this is and it also ensures, because of parallelization, that there's nothing special about L equals 200. It could very well be L equals 400, 1600, as large as you want, as long as you use enough reservoirs on enough parallelized computer cores. So the bigger your cluster, the larger the problem you can handle, which is a good thing, because if you want to be able to handle issues such as the global weather, then you're going to need a lot of computational power. And in this plot, we show that the RMS error as a function of time in the prediction phase, averaged over many trials. What this plot essentially shows is that prediction quality can be made independent of attractor dimension as long as enough reservoirs are used. So in the red curve is for predicting a Kuromura-Sivashinsky system of domain size 200, and the blue curve is the blue dashed line is for predicting a system of domain size L equals 1600. And as you can see, they lie on top of each other, those curves. So that means that their prediction capacity is the same, like, the prediction quality is the same. And the reason for that is that the red curve, for predicting the smaller domain, you use 64 reservoirs. For predicting the largest domain, you use 512 reservoirs. And the curves in between are just steps in between, essentially. Which shows that you have arbitrarily large scalability in this architecture. So as another example, we consider the Lorentz 96 model of atmospheric dynamics, which is often used for testing techniques in weather prediction. I won't go into too many details of this model, but it's a pretty common problem for testing prototype weather prediction techniques before you move on to actual high dimensional weather problems. And we find that even in this case, we can have pretty good prediction quality by using the parallelization and the scaling that comes with the parallelization. We get good prediction for about 4 or 5 multiples of the Lyapunov time, which is significant and non-trivial. And now to move on to the three-dimensional atmosphere for numerical weather prediction with machine learning. As we saw in the toy example, with a one-dimensional grid, you have domain decomposition by assigning multiple reservoirs to different sections of the one-dimensional grid. You can do that in the three-dimensional grid as well. So you can the image on the right shows you domain decomposition of the grid of a weather model, essentially, and you can actually decompose it in the same way that you did the one-dimensional grid, just with reservoir assigned to each essentially, with the overlap denoted by the buffer regions in there. So this can be extended, and what we find in this recent paper that we published in Geophysical Research Letters, where we demonstrate that this parallelized reservoir configuration can emulate the full state vector of the global atmosphere, including pressure fields, temperature fields, and up to 72 hours with significant forecast scale. So these plots are from the paper, and we are showing you just the northern hemisphere temperature at the various levels. and comparing it to climatology and persistence baselines. And we see that the machine learning model, which is the parallel reservoir configuration, outperforms climatology and persistence up to 72 hours, which is a pretty good baseline for something that was achieved with a fairly simple machine learning architecture. Yeah, this was performed using thousands of reservoirs, each of size 6,000 nodes, and it was trained using reanalysis data from the ECMWF model, 9 years of training data with time step of 1 hour. I would like to point out that this work was led by Troy Arcomano, who's a really amazing grad student and a collaborator at Texas A&M University, and is Swanson Young, his advisor, is also at Texas A&M University. Finally, it's important to note that even with parallelization, if the system is very complex, a purely data-driven approach like the one we have seen up to this point may require a prohibitive amount of training data or computational resources, and that's typically going to be true. But in many cases, we may have partial knowledge of the dynamics, which can give us an imperfect physics-based model. And if we have an imperfect physics-based model, then can we build a hybrid data-assisted model that combines machine learning with an imperfect knowledge-based model? And we have proposed that this is indeed possible. We can have a general method that leverages the advantages of machine learning and a knowledge-based model by combining the two. I won't go into too many details, but if you are interested, I can give you the reference to the paper in which we discuss this model for one-dimensional physics, and we're currently in the process of extending it to atmospheric general circulation models as well. But the idea is to combine a knowledge-based model with machine learning so that they can both work in conjunction to give you a forecasting scheme. And this data-assisted forecasting scheme, where you have a knowledge-based model combined with machine learning, can also be parallelized pretty easily in the same straightforward way that we discussed before. And lastly, so why use reservoir computing? There are more sophisticated architectures such as long short-term memory and gated recurrent units, which are used for sequence modeling techniques, and it's a very good idea to consider those architectures as well. The advantage of the parallelization technique that we talked about is that you can swap out your reservoir computing block for whatever is your favorite deep learning architecture, and you can have it work with, obviously, there are going to be a lot of trade-offs with regard to the computational time, the training time and stuff, because reservoir computing is the cheapest in terms of how much time you require to train it. So we have demonstrated some of these trade-offs in this paper with our collaborators at ETH Zurich and Themis Sapsis. I'll provide a reference at the end. What we find is that deep learning approaches certainly have some advantages for, especially when you're trying to forecast reduced order representations of chaotic dynamical systems. And there is a lot of potential for some combination of deep learning and shallow reservoir computing to improve the current state of the art in chaotic system forecasting. So that's a very interesting problem at this point, I think. This is a list of publications that has come out of this all this work. I encourage you to check it out, and please feel free to email me if you have any questions. Finally, I would like to give a shout out to all my collaborators, my advisor, Professor at UMD, my co-advisor, Michelle Gervin, Brian Hunt, and a lot of grad students and undergrads have helped with this work. So yeah, with that, I'm going to stop here, and if there are any questions, feel free to ask me.
Thank you, Patrick. Thank you, Dr. Patrick. Yeah, so because the time is limited, I think maybe we leave 1 minute for the question.
Sure.
Yeah, maybe I have a quick question.
Yeah,
for the parallel part, because I think the parallel relies on that the interaction is local. Basically, your group every four 4 new nodes into one group, then function is inside group, right?
Sorry, could you repeat that quickly?
I think it's for the parallel, you group every 4 nodes into one group for one partition. But if we have a OD, for example, ODE system, and we do not know which node interacts with which node.
Yeah, that's a really good question. Thanks, Lulu. I'm assuming that was who asked the question.
Yes, it's Lulu.
Okay, thanks. That's a good point, and that's why that is certainly a limitation of this system, where if you have global interaction, if you have global coupling between all the variables, all the grid variables, then this would not work very well at all. But the good news is that a lot of the systems that we're interested in, such as like turbulence and stuff, often have local or like short range interactions. So yeah, we cannot solve like a global interaction problem with this, but there are enough interesting problems where the interaction ranges are short. So it works in that sense.
Okay, thank you.
Thank you very much. So let's welcome our next speaker, Dr. Lu from Brown University, talking about the deep XDE.
Can you see my screen?
Yes.
Okay, yeah. So I will quickly go through the package like deep XDE for solving both fold and also inverse problems or differential equations. So when we try to use deep learning for differential equations, there are many different approaches. For example, some approaches can be applied to some specific problem, like Dodd-Hines talk for parabolic PDE in very high dimension. And also there are some approaches can be very general, and ideally it can be used to solve any problem. And in this talk, and especially for deep XDE, the method we use is based on the strong form of the PDE, and we called it physics-informed neural networks. So let me introduce the idea of physics-informed neural networks by a very simple inverse problem. In the end, you will see the algorithm actually is quite intuitive and quite simple, but in practice, this simple algorithm has been used to solve many engineering problems and achieve much better results than the traditional problem. Yeah, the problem is shown here is called invisible cloaking. Let's say we have an electric field as indicated by the arrows propagates from our left-hand side to the right-hand side. And then for the permittivity field, epsilon 1, outside domain is called epsilon 1. And inside at the center of this domain, we have a small sphere in the blue color. And the blue region has different permittivity, epsilon 3, so which is different from epsilon 1. Then due to this existence of this small region, we can see from the red figure, the downstream electric field would be perturbed. Instead of this sine wave, it will have some pattern. So this is only we have one object. But in some applications, in some optical applications, we try to add another layer, which is the pink color, surrounding this blue region. By special design, this epsilon 2, the permittivity field of epsilon 2 of this pink color, such that the downstream electric field looks like unperturbed, as shown in this figure here. So if we only look at the downstream electric field, so it looks like there's no object in the upstream. So this is application called invisible cloaking. So how can we use the deep learning for solve this problem? So basically, in this problem, we have epsilon 1 field and epsilon 3 field, and we also have the location and the size of these small spheres. Now we try to find epsilon 2, which is a function of x and y, such that the downstream phi 1, the electric field phi 1, should be equal to our target pattern. So we know this problem can be described by the Helmholtz equation. So basically, we have the Helmholtz equation for the outside domain, for the inner domain, and also for the inside domain. So for different domain, The difference is that it has different epsilon I. And of course, we have the boundary condition in between each the boundary of the, for example, for the outside, for in the boundary of the large circle and the boundary of the small circle. So we have the boundary condition of if phi1 should be equal to phi2, which is the electric field should be continuous, and also the normal derivative of the electric field also should be proportional to the epsilon 1, epsilon 2, and so on. So we have the PDE for this system, but we try to find the unknown field epsilon 2 in this PDE. But we know the solution phi1 of the one component should be equal to the target pattern of phi1 target. Basically, we have the partial observation of the PDE solutions, and we also have the PDE and boundary condition. So we try to combine both the partial observation of the solution, which is data information, together with the PDE information to infer what's the unknown permittivity field. So this is the basic idea of physically informed neural networks. And to achieve this, first we have a neural network, which could be standard fit-for neural network or ResNet or other types of neural network. The input of the network is X and Y. Basically, we consider in the 2D case, which is the X coordinate and the Y coordinate. And for the output is our unknown solution, phi1, phi2, and phi3. These three fields are the solution of the PDE. And more importantly, we have the unknown epsilon 2 field, which is our target unknown function. Then we design our loss function to train the network. So for the first part, we know we have the data information for the solution of phi1 in the downstream. So the first loss function is a standard, could be mean square error between phi1 and phi1 target. And we also embed the PDE into the loss function, which means, so we know the phi1 should specify the Helmholtz equation, or as shown here. Then we can evaluate so initially, the neural network is random initialized. Then phi1 definitely could not satisfy this Helmholtz equation. Then we can select the random points on the outside domain and evaluate the mismatch or mismatch of the phi1. So how basically what's the residual error of the Helmholtz equation? We can use this component as another loss, and so on. We can also have the loss components from the boundary condition. So in this framework, as you can see, so it's very simple. Basically, we try to make the network satisfy the data information, satisfy the PDE, satisfy the boundary condition, and all components goes into the loss function, and then we train the network to have both the solution and also unknown field. But as you can see here, this method is mesh-free and also particle-free. So it's very simple. We do not require to draw any mesh to solve these partial differential equations. And you can seamlessly integrate the information and the physics. So here the physics is PDE, but we can also consider other types of physics. For example, the mass conservation, momentum conservation, or even more complicated physical laws. So any kind of physical laws can be ideally transferred to it can be embedded into loss function. And also in the application here is the standard PDE. And in our paper, we demonstrate that this framework can be extended to other types of PDEs. For example, for the fractional PDE and also stochastic PDE. So after we train the network, as we can see, we can correctly infer the epsilon 2, the unknown field of epsilon 2 for the inner circle, and also with the correct electron field on the whole domain. So this is a very simple case. Let me show you another video. Can you see my video, right?
Yes, we can.
Okay, yeah. So this is a talk from the CEO of NVIDIA, Jason Huang. So NVIDIA there's a group in NVIDIA, they have also applied physically informed neural networks into the design of the chips. This is their simulation. As you can see, so this is a fluid flow, and they design different chip domain. So this is just application. So this is a real application has been used in engineering and in practice. So let's go back to my slides. So let's go to some theoretical understanding of this network, of this methodology. So first, when you try to use a neural network for solving PDEs, then first question is whether or not there exists a network such that the error of the network and our true solution of the PDE can be arbitrarily small. So the answer is yes. So this has been basically proved by Pincus in 1999, which it means the neural network can not only be used to approximate a function, which is the universal approximation theorem, but it can also be used to approximate the partial derivatives of this function simultaneously. So I will not go into the details of this theorem, but it basically means the neural network is very powerful. It can be approximated the partial derivatives and also the function itself simultaneously. So this is existence. And recently our group has another paper shows that when we do this physically informed neural network, actually we can have some error bounds. So I will not go into the details of that paper. And here's another slide, which means I just want to show when we try to use the network to train, when we try to train the network, what's the training procedure of the network? Let's compare two different scenarios. The first is the standard supervised learning. We try to use the network to approximate a standard function. It's a summation of 5 sine waves. Then we use the training. If we monitor the training procedure of the neural network from the frequency domain, then we can see from the left figure, if we check the five different frequencies, then we can see the low frequency feeds first and then high frequencies. Basically, the neural network feeds the low frequency of the target function and then feeds low frequency during the training. But if we try to use neural network for solving PDEs, because currently our neural loss function has the partial derivatives of the neural network, has the PDE loss. Then in the right figure, we numerically show that the training procedure would be totally different. So in the left figure, it shows that all the 5 frequencies would be learned simultaneously. And more interesting, we can achieve faster learning to achieve the small accuracy for all the frequencies compared to the standard supervised learning. Which means if we have the derivative of the loss of the function into loss function, then the training can be faster. And another issue in practice is that when we try to train the neural network, we have to sample some residual points for the loss function. For example, for the Burgers equation, in this 1D Burgers equation, when we try to use neural network to solve this 1D Burgers equation, then we need to random sample some locations to compute what's the loss function. So usually we do the uniform sampling as shown in the black dots here. But as you can see, for this Burgers equation, the uniform random points definitely is not sufficient enough or is not efficient, because we know the Burgers equation, the solution is very sharp on this x equal to 0 locations. So ideally, we should add more and more points on this domain, which is quite similar to the adaptive refinement in the found element method. And what we did here, during the training, we adaptively add more points in the locations while the PD residual is large. So basically, during the training, for example, every 10,000 iterations, we check in which location the loss function is large. Then we add more and more points on those locations. So in this way, we can dramatically reduce the required number of training points. For example, for this 1D Burgers equation, if we use uniform training points, then we need roughly 10,000 training points to achieve 1% error. But if we use this adaptive way, we can reduce the number of training points from 10,000 to roughly 2,000. So this is the method part. Next, I will go briefly introduce the software called DeepXDE. So when we try to use this package DeepXDE for solving the differential equations, basically it has a few different modulars. For example, the geometry modular, the equation modular, and also boundary condition, initial condition, and network modular. The users only need to define each component, and then everything is automatically handled by the package. So it's very convenient. For example, let's say we try to solve a 2D Poisson equation in an L-shaped domain. Then by using DeepXDE, so the first step, let's define, okay, our geometry is a polygon. Then we define what's the PDE. Basically use the TF.gradients. So we say the PDE is the y, the second order gradient of y to the x, and minus the y to the this y should be u, the solution. So the du dx, the second order, and also second order du dy, and then minus 1. Basically, this is the equation. And then we say what's the boundary condition, okay, with the district boundary condition, and then what's the value of the district boundary condition. Then we define how many training points we require is 1,000, and then we choose what's the network. For example, we can choose the fit-for network. Then we can compile, choose the Adam, the algorithm, the training algorithm, also with the learning rate 10 to the minus 3, and it will be trained 50,000 epochs. Basically, we define the problem by using the API provided by DeepXDE. That's it. Then we can have the solution as shown here. And also the time-dependent problem, or a system of ADE, or a system of PDE, or inverse problem. Oh, this is IDE problem, basically integral problem, integral differential equations, or inverse problem, which as I showed in my first example. So all these problems can be handled very easily using the package DeepXDE. And one feature I just want to mention is that in practice, we may have very complicated geometry. For example, as shown here, our PDE can be defined on this geometry. Then in DeepXDE, this kind of geometry can be defined by 3 basic operations: union, difference, and intersection. For example, this geometry basically can be defined by union, difference, and interaction from 4 basic geometry: the polygon, circle, and the rectangle. So all these I call primitive geometries has been predefined. Then we can use this predefined geometry to define complex geometry. So it's basically that's my talk. So DeepXDE can be installed either through the PIP or Kona, very easily can be installed, and it has been downloaded more than 30 times and lots of GitHub stars. So if we have any question about this package, and if we have any suggestions, you can submit the GitHub issue or pull request. Yeah, thank you.
Thank you very much, Dr. Lu. Any questions? Yeah, I think this is excellent work because it has already been used in the industry applications.
Yeah, so the software, I would say, it can be very convenient to use for many different applications. But and also, the software package here is well structured and highly configurable. So even if in academia you try to modify some component of this algorithm, of this package. For example, you have a new idea of how to implement the boundary condition or initial condition, or have a new idea of the training procedure. Then what you need to do is you only need to go to the specific modular of the software without modifying everything else. Then you can make it work. So it's well structured, and each component is loosely coupled.
Excellent. Are all these packages based on the TensorFlow only, or are you considering like sharing other platform like Signal or yeah?
So currently, the package is based on either TensorFlow 1 or TensorFlow 2. So basically, it supports both TensorFlow 1 and TensorFlow 2. Mm-hmm. And I plan to add the support of PyTorch. Mm-hmm.
Yeah, because more research work like in academia is using PyTorch, although like TensorFlow is more based on engineering part. Yeah.
Yes.
Yeah, excellent.
Yeah, but another thing is, if you try to use this sort of software to solve some problem instead of modify the software itself, so you do not need to know lots of TensorFlow grammars. So the key TensorFlow grammar you need to know is tf.gradients to compute the gradient. Basically, that's it. So everything else is inside the software.
Yeah.
So I have a quick question.
Yes.
So like how many dimensions in your system can you impute? I saw you 2 dimensions, 3 dimensions. If I have 5 or 10 dimensions, is it possible to be done efficiently?
So for high dimension, definitely I would say it's doable, but in practice, the computational cost would be expensive if we go to high dimension.
I see. So even with the neural network that you set up, so like there's so there's still potential to reduce the dimensions in the future, right?
Yes.
Like dimension reduction part.
Yes, compared to the standard method like find element, yeah, definitely we have the advantage of in high dimension, but I'm not sure. So how much high dimension we can go, because
I see.
In my problem, usually I consider 2 dimension or 3 dimension.
I see. Thank you.
But yes, definitely we can do better in high dimension than standard method, but there's no guarantee the accuracy in very high dimension.
I see. Thank you.
Thank you. So any other questions? Okay, so thank you all very much for sharing your excellent cutting-edge research work. I like this online mini symposium session pretty much. I will upload our video so that we can have more details understanding and have more discussion maybe offline, and hope to learn and discuss more research work in future with you. Again, really appreciate your joining this online meeting. Thank you very much.
Thanks, Ting, and everyone else. It was a really nice organization.
Thank you. Thank you very much.
Thank you all. Thank you. Bye.
Thank you. Bye.
Bye. Bye.
Thank you.
Take care.
Bye.
Bye.
You take care.